All right, here we go. Intro video for Chapter 8. So this is going to go as Section 8.1, um, which is just really just kind of an introduction to number patterns that we call sequences or series. So a lot of this chapter is going to have to do with formulas. This is kind of the one section of the chapter that doesn't deal real heavy with formulas. It's mostly just getting an understanding of sequences and series and working with those things. So if you got your journal, we are going to start on page 218. If you want to follow along. So top of it looks like this. So we're not going to define all these. I'm going to explain a lot of this as I just kind of go through a couple sample problems here. So a sequence is just a pattern of numbers. And so that's kind of the main idea here is we're looking at number patterns. One thing to get out of this is the first value is your first term. This would be your second term, your third term, your fourth term, and so on. So n represents the term number, and then a of n would represent the value of that term. So take a look at this one. So this would be, they call this a finite sequence simply because it ends, whereas an infinite sequence has the little dot, dot, dot that means it goes on and on forever. But if you look at this, this would be our first term, our second term, our third term, and our fourth term. So our first term is 2, second term is 4, so on and so on. So again, the term number is what we call n. So our first term has a value of 2, our second term, our third term, and our fourth term. So n represents the term number, and then a of n represents the value of that term. So we would read this as the first term is 2, or the second term has a value of 4, so on and so on. So that's just kind of the basic description of these guys. One of the really challenges of this first section is coming up with a description of this pattern in terms of n, or something like this. So one of the things that we'll be doing is in order to come up with a statement like this, which is what they call the rule of the sequence, we would say something like, what are we doing to n in order to get a of n? In other words, what are you doing to 1 to get 2? What are you doing to 2 to get 4? What are you doing to 3 to get 6? On and on and on. And if we look at that, we can say, oh, well, I multiplied by 2. And I see that that works for every single case. Then that can be my rule. And so we would say my rule is 2 times n, right? Because if I take my n and I multiply it times 2, I get the value, right? So it's 2n. So anyway, that's one of the things we'll be looking at here in this first section. If you flip it over to the second page, one of the things that we deal with on these guys is whenever you have the numbers laid out with a comma. So if I said 2, 4, 6, 8. So whenever you lay them out with a comma, then this would be called a sequence. If I add all these terms together, like this, then it becomes a series, right? Because now we're actually finding the sum of all those numbers. And this is where you get introduced to this really fancy Greek letter sigma that you see right there. Kind of looks like an E, but it's the Greek letter sigma. And so we're going to work a little bit with that. Let me just give you sort of the general idea behind sigma notation, or they call it summation notation, is what you're seeing on bottom is the term that you are starting with. So this says I equals 1. That just means I am starting with the first term, and I am ending with whatever this is, which would be in this case the fourth term. So in other words, I'm going to find the sum of terms 1 through 4. And you can see that's what we're doing. We're finding the sum of the first 4 terms of that sequence. The guy that you see on the right is the rule, right? It's the rule of this sequence. I don't know why they use an I sometimes. Sometimes they use an I, sometimes they use an N. I wish they just used N all the time so it wouldn't be confusing, but here I'll even put a little N there for us. So it looks the same as what we're seeing on the last page. So again, I'm finding the sum of terms 1 through 4. This is the rule. If I didn't know what these numbers were and this is all I was given, I would find my 4 terms by plugging the numbers in for n. So if I put a 1 right here, well, 2 times 1 would give me my first term. If I plug a 2 in for n, 2 times 2 would give me my second term, and I could then plug in a 3 and a 4 in order to figure out what the 4 terms are within that sequence. So we're going to see a little bit of that as well. Let me take you to some actual problems here. So I'm jumping over to page 220 for this stuff, and I'm going to take you through a few of these guys. So the first part of this, real simple. If we're going to write the first 6 terms of the sequence, again, n represents a term number. So if I want to find the first term, I simply plug in a 1 for n. So if I plug in a 1 and simplify that, then I figure out what my first term is. The first term they would write as a of 1. That just represents the first term is 0. If I want to find the second term, then I'm going to plug in a 2 for n. And if I simplify that, that tells me my second term is 7. If I want to find the third term, then I plug in a 3 for n. And 27 minus 1 is 26. So they want us to do that. They want us to do that for the first 6 terms. So I would have to plug in a 4 to get the fourth term, 5 to get the fifth term, 6 to get the sixth term, on and on and on. So you get the idea. So that's how we find the first 6 terms of the sequence. That's how you find any term of the sequence, right? If I wanted to find the 20th term, well, I would just put a 20 in for n, and then I could figure out what the 20th term is. And so that's kind of the real basics of just plugging in some numbers. This is the one that can be really tough, is trying to write a rule for the nth term. Describing the pattern is usually pretty simple. It's figuring out the rule, which is like something like this. This would be considered the rule of a sequence, right, in terms of n. But as I look at this, so just describing the pattern, like I can see, well, it looks like I am adding 2 every time to get the next term of the sequence. Right? You can see that works all the way through. So real simple. That would be this guy. That would be the description of the pattern, would be to say, well, I'm adding 2 every time to get the next term. The next term, well, if I add 2 again, I can see that my next term in the sequence would be 5. So I'm using my description in order to get the next term. The rule is the tricky guy. So think of, I'm going to rewrite this to give myself a little more space. So my values are -3, -1, 1, 3. So remember that the first one represents your first term. This is your second term, third term, and this is your fourth term. So in order to get the rule, the best way of looking at that is to say, what am I doing to n in order to get a of n? What are you going to do to 1 in order to get -3? Well, I could multiply it by -3, but does that work for the next one? Right? It doesn't. So okay, so it's not multiplying it by -3. We could say, well, I subtracted 4. Does that work for the next one? No, it doesn't work. So it's got to work for all of them in order to be the rule. With some of these, and what makes some of these kind of tough, is sometimes it's not just one operation. Sometimes you have to multiply and then add, or you can raise it to an exponent and then subtract. Right? So sometimes it takes 2 operations in order to get the rule for this, and that's when it gets really tricky. So on this one, I had to play around with the numbers quite a bit until I figured out that the rule for this was 2n minus 5. Right? And so you can see if you test it that this rule does work. So if I plugged in a 1, so if I said 2 times 1 is 2, minus 5 is -3. Right? And you can test any of these numbers and they're going to fit if I plug them in for my rule here. So this can be a pretty tricky process to do these guys, but These are the kinds of rules sometimes we would come up with for this. And some of these, don't get too frustrated with them. Sometimes you just got to play with them a little bit, give them a shot, try them. If you can get it, great. If not, no big deal. For the rest of this chapter, we're going to be using formulas. So it's just kind of like, for those of you who like like kind of solving a puzzle, that's kind of what it's like. It's just sort of like figuring out a puzzle. Let me show you one more. So on this one, let's see. Again, I am adding 2. So my description is the same. My denominator is not changing. So that actually makes part of this rule kind of easy. I can see in my rule that the denominator is always 5. So there's the bottom part of my rule. All I have to figure out is what's the top of my rule? What's the numerator? How did I go from 2 to 4 to 6 to 8? And so again, the way you have to look at it is, that's my first term, second term, third term, fourth term. So what am I doing to 1 to get 2? What am I doing to 2 to get 4? What am I doing to 3 to get 6? And this is one I think you guys should be able to figure out. So hopefully you can see that I'm multiplying by 2 every time. If I did 2 times 1, I get 2. 2 times 2, I get 4. 2 times 3, I get 6. So I'm taking my n value and multiplying it by 2. And so that would be my rule for this sequence. Summation notation is the one that looked like the weird little, this Greek letter sigma that we have. So all you have to do for sigma notation, I'm just going to use this one because I already have the rule. In sigma notation, the rule goes to the right of it. So my rule is 2n minus 5. So, and that's actually the hardest part of this, is in order to do this, you have to first figure out the rule. So, but anyway, that's the rule. Again, we're going to say I am starting with my first term. So I'm going to say n equals 1. And how many terms were here? This one says ... which means this one goes on forever. So in a case like that, if it goes on forever, we're going to say it goes to infinity. For something like that. If there was a specific number of terms, like let's just say it ended. Let's just say there was no ... right? And there was only 4 terms. And so it looked like this. It was just, that's it. That's the end of it. There's only 4 terms. Then I would put a 4 right there instead. So let's do that with this one. So let's just say there was no ... here. So pretend for a minute that there's only 4 terms in that sequence. We would say, okay, here's my sigma notation. I can see the rule is 2n over 5. And I started with my first term, so n equals 1. And I went all the way up to my 4th term, so I put a 4 on top. So again, this tells you what term you started with, this tells you what term you ended with, and this is the rule of the sequence. So that is summation notation. Last part. Let me show you number 7. Let me show you number 6. So if I wanted to find the sum, how would you find the sum? So this would tell you that to start with n equals 2 and go all the way up to 5. So I would have to start by plugging in a 2 for n. So 2 over 2 minus 1 plus, and then I got to plug in a 3 for n, because remember this means I'm going to go terms 2 through 5. So if I plugged in a 3, then I get 3 plus 3 minus 2. Or 3 over 3 minus 2. 3 minus 1, sorry. I'm looking at that 2 right there. Then I plug in a 4 for n. And then plug in a 5 for n. So again, I'm just plugging in numbers 2 through 5. And then if I just add all those results together, I have my sum. One more thing I wanted to show you. Okay. So never mind. I was looking back at my notes from last time, and these guys are good. So again, if you wanted to find something like this would be a little lengthy because you would have to plug in terms 1 through 18 to find this. So that would be a little rough. You'd have to plug in a 1, so 1 squared, then 2 squared, then 3 squared, all the way through 18, and then add those 18 answers together. So that would be a little rough. If you do have one of the, if you had a graphing calculator, and I know some of you do, let me show you. There is actually a tool on there that you can use. Which is kind of neat, but again, you don't have to do it this way. It's just kind of a fancy tool. If you have this, if you go under this math button and scroll all the way down to summation, it looks like that, and all you got to do is plug in the info. So I use this button right here for my n or my x or my I, whatever it is. So x equals 1. I'm going to go up. There are 18 terms. And the rule, and the entire rule must go in those parentheses. So it is x squared, and just hit enter, and there's my sum. So it's kind of cool, kind of a cool feature, but you wouldn't need to do it that way. That's just kind of a cool feature on some of the new calculators. But that's it for the intro. The rest will be using some formulas and all that fun stuff. So until next time.